aldol reactions in which we start with two different aldehydes, for example ethanol and propanol, using the classical condition sodium hydroxide, water, we obtain mixture of four products. Ethanol condensed with itself to give one product. Propanol condensed with its enolate to give another product. The enolate of propanol condensed with ethanol, third product. The enolate of ethanol condensed with propanol to give the fourth product. Such mixture of products are difficult, very difficult to be separated. Therefore, this type of reaction has no significance in organic synthesis. We overcome these difficulties by two approaches. First, when we use the classical method of using sodium hydroxide in water or sodium ethoxide in ethanol, in this method we starting with two aldehydes, one of them containing no alpha hydrogens, for example benzaldehyde, and the other aldehyde has alpha hydrogen, for example propanol. This one step. Second step, we add the solution of propanol, aldehyde containing alpha hydrogen, to a mixture of benzaldehyde and sodium hydroxide. Slowly. Under these conditions, benzaldehyde does not condense, does not undergo self-condensation. Under this condition, benzaldehyde does not undergo self-condensation because there is no enolate. And the propanol will be present in the reaction mixture mainly as enolate because we add it slowly. This enolate has low probability, low opportunity to self-condense with the original aldehyde, but condense it or react with the benzaldehyde to give, followed by dehydration to give the condensation product, aldol condensation product, as main product. Here we name the product 2-methyl 3-phenyl 2-propanal. Another example of benzaldehyde, aldehyde containing no alpha hydrogen, phenyl acetaldehyde. Here is alpha hydrogen. The product would have been formed 2,3-diphenyl 2-propanal. Always note the ending enal. We see also that the addition is accompanied by dehydration to form the conjugated double bond because it's stable, stabilized structure. Always dehydration is favorable when extended double bond is formed. Here, reaction of formaldehyde, which contains no alpha hydrogen, and 2-methyl propanal using the classical condition to give the aldol product, aldol addition product. Here no dehydration takes place because no double bond would have been formed. We can use ketone instead of aldehyde containing alpha hydrogen. Under these conditions, classical conditions, ketone cannot self-condense because the addition step is sterically hindered. Therefore, the opportunity is high, very high, to the reaction of enolate from ketone with benzaldehyde. For example, here acetone with benzaldehyde give 4-phenyl butene 3-ene 2-one. Very good yield. Benzaldehyde with C2-phenol ketone, and under the classical condition gives 1,3-diphenyl propene 1-one. We always note the ending en-on. Problem outlined below the synthesis of a compound used in perfumes called lillyl aldehyde provide all the missing structures. Here tertiary butyl benzyl alcohol plus pyridinium chlorochromate in dichloromethane gives the aldehyde oxidation primary alcohol. Oxidation on primary alcohol gives the aldehyde. Then we added propanal sodium hydroxide. This is crossed aldol reaction between aldehyde which contain no alpha hydrogen and aliphatic aldehyde. We note that the enolate formation take from the adjacent methylene group because it is the acidic group, acidic methylene group, acidic proton here. Then aldol addition takes place, it's normal, followed by dehydration because formation of extended conjugation. The last step is reduction of the double bond by hydrogen in palladium. Condensation with nitriles. Nitriles containing the methyl oder methylene group, as for example acetonitrile oder phenyl acetonitrile, as in this example, have acidic hydrogen. For example, the pKa of acetonitrile is 25, and therefore this nitrile can take place the aldehyde with alpha hydrogen and undergo addition reaction of the aldol type. The addition product can undergo dehydration to give the extended double bond, as this example illustrates. Nitroalkanes also have the H adjacent to the nitro group is acidic. The H is acidic, which besides the nitro group, pKa of nitromethane, for example, is about 10. Therefore, also can condense the enolate of this nitroalkane generated under the classical condition using sodium hydroxide water. This enolate can condense with aldehydes in aldol type reaction. to give the nitro compound which can be reduced easily to the amino group. The second approach to the difficulty of formation of many products in the cross-Aldol reaction is to use or to generate lithium enolates under the condition of kinetic control. That is to say, to generate the kinetic enolate, lithium enolate, using LDA in a product solvent. Here, one of the aldehyde is nearly completely converted to enolate under this condition, and have low probability, low opportunity to self-condense, but react with another aldehyde to bring the addition product. For example, here the ketone is added to lithium diazomylamide, strong base, which remove alpha hydrogen from the ketone to produce an enolate nearly completely. There is low opportunity for self-condensation of this ketone. Then aldehyde is added to the enolate then the aldehyde react with the enolate. The enolate is added to the aldehyde group. Protonation of the formed alkoxide gives the product. We notice here that no dehydration takes place because no extended conjugation can be formed. Another advantage of using lithium enolate generated under kinetic controlled reaction, that's to say, generation of kinetic enolate, is the regoselectivity. We have learned that kinetic enolate is generated from the less statically hindered position, because the base used is bulky base and very strong. Therefore, the less accessible, the more accessible proton of hydrogen to remove is the less sterically hindered. For example, here ketone, methyl ethyl ketone, we add lithium diisopropylamide tetrahydrofuran at minus 78. The less hindered proton of the methyl group will be abstracted by the base, strong and sterically hindered base, to give the enolate. Mainly, this enolate react with aldehyde, for example acetaldehyde, to give the alkoxide, which can be protonated from water. Here we notice that single crossed aldol product results. Here also no dehydration takes place because there is no extended double bond formed. If we carry the last reaction using the classical method, used for aldol reaction, that is to say sodium hydroxide in water or isoxide in ethanol, we obtained mixture of two products. One comes from the reaction of kinetic enolate from the least hindered position, that's to say kinetic enolate, and the other product, second product, results from reaction of thermodynamic enolate with aldehyde. For example, here the last example, but we use different condition. The condition of very strong and sterically hindered base in a protic solid. Sorry, we use the classical condition of using sodium hydroxide in ethanol in water to give the mixture of kinetic enolate and thermodynamic enolate. Each enolate react with the added aldehyde to form the product. Therefore, we obtain a mixture of crossed aldol product. A problem: outline directed aldol synthesis of the following compound. Here we apply the strategy of retrosynthetic analysis. We identify the CC bond bearing the hydroxyl group. This bond might have been formed by an aldol addition reaction. from this starting point we can identify the enolate and the aldehyde. Here, as indicated, is a carbon bearing the carboxyl, and then our aldehyde component is the acetaldehyde plus this enolate. This enolate, lithium enolate, because the problem say that directed aldol synthesis. Therefore, we use lithium enolate. Lithium enolate can be generated from the corresponding ketone here by lithium diazoborobylamide followed by addition of the aldehyde, and then the last step, addition of water to transform the alkoxide to the aldol product. Cyclization by aldol condensation. Aldol condensation it's to say intramolecular aldol condensation can be used to form cyclic ring compound. Why? Aldol reaction of two aldehydes or aldehyde and ketone or diketone, either dialdehyde, aldehyde, aldoketone or diketone. Before we consider this example, we should remember that 5-membered rings form far more readily than 7-membered rings, and 6-membered rings are more favorable than 4 or 8-membered rings when possible, when the formation of these rings is possible. Here our example is ketoaldehyde treated with sodium hydroxide form 73 of the methyl bentenyl ketone. Here the important thing, more important, is the reaction mechanism to account for the formation of this product. Here in the starting ketoaldehyde, we use the classical method of using sodium hydroxide, water. Sodium hydroxide can form enolate, can abstract the proton from more than position, from here, beside the ketone, methylene beside the ketone group, and from the methyl beside ketone group, and from the methylene beside the aldehyde group. But one of these key enolate, which is the enolate formed from methylene beside the ketone, is formed favorably because it is thermodynamically enolate. Thermodynamic enolate here from the ketone. And this stable enolate formed mainly at major product attacks the aldehyde group in equilibrium reaction to form the addition product, 5-membered ring addition product. The enolate from this ketone, from this group, methyl group of the ketone, formed in as minor product, but when it reacts with the aldehyde group, would have formed 8-membered ring, and this reaction is not favorable. Remember that all of these reactions are equilibrium reaction. The more stable product which will predominate. Note that also the possible formation of the enolate beside the aldehyde group, that's to say the enolate from the methylene beside aldehyde group, leads to very little amount of the product, because if it is formed, would have react with the ketone in an equilibrium. We have two reaction, competing reaction. Reaction of the enolate from methylene beside the ketone with aldehyde. That's very favorable reaction because attack here on the aldehyde group. Another competing reaction is the enolate beside the aldehyde group attack the ketone group. The first reaction is more favorable because aldehyde group is more reactive than ketone group, as we have learned. Therefore, this 5-membered ring formation in this way is the favorable reaction. Remember that all reaction, remember again that all of these reactions are in equilibrium, and the reaction which lead to the more stable product will form it as main product. Then the alkoxide formed, the alkoxide anion formed from the aldol addition, abstract proton from water to give the intramolecular addition product, which can lose proton and hydroxyl here, that's to be dehydrated in the presence of alkaline medium to form the double bond, conjugated double bond, therefore stabilize the double bond. That's to say, base promoted dehydration leads to product with conjugated double bond. Here is the mechanism. Addition to alpha beta unsaturated aldehyde and ketones. Nucleophile add to alpha beta unsaturated aldehyde and ketones in two ways. First, the nucleophile attack the carbon of the carbon-oxygen bond as usual. Is to say, simple addition product. The second way, the nucleophile attack the beta carbon in what's called conjugated addition reaction. The product called conjugated addition product. To give the ketone. We can account for this behavior of alpha beta unsaturated ketone by considering the resonance structure of this group. Here, in the three resonance structure of alpha beta unsaturated aldehyde or ketone, there are separation of a charge into structure, positive charge on carbon into structure, and oxygen and negative charge in the oxygen in these two structures. Positive charge at carbon of the carbonyl group and positive charge at carbon at the beta carbon. The resonance hybrid is a structure which bearing partial negative at oxygen and partial negative at carbon attached to oxygen and partial carbon at the beta carbon. Therefore, the nucleophile add to carbon of the carbonyl group or the beta carbon. The way in which the nucleophile add to this group depends on the type of the nucleophile in most cases. If the nucleophile is a strong nucleophile, for example, Grignard reagent, methyl Grignard reagent, or alkyl lithium. The nucleophile add to the carbon of the double bond, of the carbonyl double bond. If the nucleophile is weak, such as cyanide or enolate of the aldehyde or ketone, then the nucleophile add to the beta carbon. We have just seen the example of Grignard reagent, which add to carbon of the oxygen of the carbonyl group as the major product. Here, cyanide ion, weak nucleophile add to the beta carbon to form the ketone in 95%. Here, the mechanism of conjugate addition to alpha, beta unsaturated aldehyde and ketones using the weak nucleophile cyanide ion. Cyanide ion attack the beta carbon at the electron of the double bond shifts to the oxygen to form the enolate intermediate. The enolate accept proton directly to form the ketone form, or accept the proton on the oxygen to form the enol, and enol transforms to in equilibrium to E2 form. Here at this time, you should remember the order of nucleophilicity of the common reagent to help you to predict the major products from such reaction. Order of nucleophilicity of the common reagent is the following: alkyl of the Grignard reagent and the butyl lithium, the alkyl lithium in one category, is stronger nucleophile than lithium diisopropylamide, stronger than cyanide anion, stronger than the enolate, which is the conjugate base of the aldehyde or ketone. The enolate is a stronger nucleophile than the alkoxide, which is more stronger than hydroxide ion. This order is the opposite of the order of basicity which we identify by considering pKa of the conjugate acid of these bases. For example, alkane, pKa of alkane about 50, pKa of diazopropylamide 33, amine like primary amine like diazopropylamide, pKa of hydrocyanuric acid 25, pKa of alpha hydrogen aldehyde and ketone 19, pKa of alcohol 18, pKa of water 16. Here is an example of addition of weak nucleophile primary amine, thilamine in water to alpha beta ketone, which gives about 75 of the addition product at the beta carbon. The mechanism involved in the last reaction of primary amine with alpha beta unsaturated ketone is the following. Here amine as nucleophile attack the beta carbon, then as the proton at the hydrogen abstracted by the nitrogen go to the oxygen to form the enol form. This transformation takes place in two separate steps. Proton is lost from the nitrogen atom and a proton is gained at the oxygen to form the enol form. Then enol form transformed in equilibrium to the keto form. We noted that always here the keto form is a major product. The conjugate addition of enolates to the alpha beta unsaturated aldehyde ketone. Enolate, as we have said, is a weak nucleophile, which most cases add to the beta carbon. Here is an example. Cyclohexanone treated with ethoxide form the enolate. Enolate attack as the beta carbon. The electron of the double bond shifted to the oxygen to form the enol. Then to form the enolate. Then the enolate is protonated by proton transfer from the solvent, ethyl alcohol. To give the enol, and enol transform it to ketone. Or enolate gives directly the ketone as keto form. This is called Michael addition. Here is a problem. Which illustrate application of conjugate addition to alpha beta unsaturated aldehyde to give a heterocyclic compound. The first step is, in this problem, the attack of nitrogen on the beta carbon, and then the formed ketone reacts with the another nitrogen to form C double bond N. We have studied these reactions in the nucleophilic addition of amine to the carbonyl compound. I repeat, the one nitrogen, the amine attacks the beta carbon to form the aminoaldehyde, undergo intramolecular condensation reaction to form the N double bond C. The compound is called dihydropyrazole. Here, the reaction of enamine with alpha beta unsaturated nitrile. The cyano group here, the nitrile group here acts as carbonyl aldehyde and ketone, and it activates the beta carbon by resonance hybrid identification. If you write the resonance structure of this cyanide, this nitrile, you recognize that the beta carbon has partial positive charge. Enamine because of resonance has nucleophilic carbon of the double bond. One of the carbon of the double bond is a nucleophilic carbon and can attack it will attack the beta carbon in alpha beta cyanide. To results in alkylation of this enamine. Hydrolysis of enamine bearing the positive charge results in the formation of ketonic group. If you write the resonance structure of enamine, you will recognize that the one of the carbon of the double bond is nucleophilic, and this is a useful character of enamine. Which are exploited in this reaction, Michael addition, and can be used for acylation or alkylation of enamine. Here in this slide is another example of base catalyzed Michael addition. The methylene group here between the ester group and the carbonyl group is much acidic than the proton besides the only carbonyl group. The pK here about 9, 10, in case of ketone and aldehyde about 19. Therefore, enolate can easily be prepared by using sodium isoxide. Enolate added to the beta carbon of the ester, as in case of double bond. The triple bond there takes the place of double bond to give the enolate intermediate, which then accept proton from methanol to give the final product. alpha beta unsaturated ester. Problems. What product would you expect from the base catalyzed Michael addition of the following? First example, it is direct example of Michael addition. The base will generate the enolate from acetophenone. This enolate attack the beta carbon of enone to give the carbanion, which can intermediate enolate. Sorry, give the enolate intermediate, the formed carbanion from acetophenone as enolate will attack the beta carbon of the enone to give another enolate intermediate, which can accept the proton from the medium to give the final product, which will be 1,5-diphenyl bent 1,5-dione or 1,5-diphenyl 1,5-pentadione. Number B. 1,3-diphenyl 2-propene 1-on, the same ketone with cyclopentadiene. Cyclopentadiene, the methylene have the methylene group, which is acidic. The methylene group in cyclopentadiene is acidic because the conjugate base, the formed anion, the formed carbanion from it is stabilized. This aromatic structure is stabilized. Therefore, under the base catalyzed condition of Michael addition, this proton will be removed to form the carbanion, and the carbanion attack the beta carbon as normal in Michael addition to form the end product 1,3-diphenyl 3-cyclopentadienyl propanone. Additional problems. What products would form when 4-methyl-benzaldehyde reacts with each of the following? Acetaldehyde, alkaline medium, sodium hydroxide. This is direct example of aldol condensation. The enolate will be formed from acetaldehyde. This enolate attack the aldehyde group to form another enolate, which accept proton from the medium to form the aldol addition product beta hydroxyaldehyde, which will be dehydrated to form the double bond here with an extended double bond, extended conjugation. Therefore, dehydration is easy by the alkaline medium. To form the product, 3-phenyl 2-propenyl is enal. Note the end, enal. Another example, Grignard reagent, then acidified. This is addition reaction to the aldehyde group form the, after acidification, the secondary alcohol. One phenyl propanol. Number 3, cold dilute the simple manganate alkaline medium. Under this condition called, the only oxidized group is the aldehyde group to give the benzoic acid, para-methyl benzoic acid. Or 4-methyl benzoic acid. Hot dilute both the aldehyde group and the methyl group are oxidized to form dicarboxylic acid called 3-phtalic acid. The last one example, the last reaction, it's phytic reaction between these simple elite and the carbonyl group, aldehyde group of the 4-methyl benzaldehyde. Note that the methyl group here in all of this reaction except reaction D are inert under these conditions, therefore doesn't react. Additional problems. What starting compound would you use in an aldol cyclization to prepare each of the following? Number A, here, B, C. This type of questions, we use the approach of or the strategy of retrosynthetic analysis as follows. First example here. . We recognized the double bond here, inner double bond, would have formed from hydroxyl group beside or adjacent to acidic proton. This hydroxyl alcohol come from aldol reaction, intramolecular aldol reaction. So simply the synthesis, this diketone treated with sodium hydroxide water, the anion would form it from here or from here. If the anion formed from here, it would attack the ketonic group to form the aldol addition product. Under this condition of the alkaline medium, OH abstracts the proton here, abstract this proton, acidic proton, hydroxyl group will abstract this proton because it is acidic, to form the alpha beta unsaturated ketone, enon, and water is formed. Sodium hydroxide will be again liberated. Another example, the same strategy, retrosynthetic analysis. Here. We recognize the double bond here. Comes or results from hydroxyl group here and acidic H here. This is here. This product would be formed from our Y aldol reaction between this ketoaldehyde alkaline medium, sodium hydroxide here. Then the synthesis, the last one in the retrosynthetic analysis will be the first one in the synthesis. The last one in retrosynthetic analysis, the last compound in retrosynthetic analysis would have been the first one in the actual synthesis. This ketoaldehyde. Sodium hydroxide ethanol gives the aldol product, aldol addition product, intramolecular reaction, intramolecular aldol addition reaction, intramolecular aldol addition reaction. This protein is acidic, can be abstracted by methoxide to form the double bond and liberate the methanol. And sodium hydroxide. Here another set, the last set of addition problems. Predict the products of the following reactions. Here, first one, cetophenone, iodine, excess iodine, sodium hydroxide, water, then acidify. In the first step, that's haloform reaction. First step is substitution of the proton of the hydrogen in the methyl group to form triiodo. Derivative, this in the alkaline medium can neutralized to give the carboxylate, benzoate, and the iodophore. The acidic medium, benzoate, sodium benzoate here is converted to the benzoic acid. Second example, is an aldol condensation product between one molecule of this ketone and first one molecule of this to give the addition product of this carbonyl at this first aldehyde group and this carbonyl first aldehyde group. This is one molecule from here. Then remains two sites for carbonyl formation. Another molecule will react in the same way as the first molecule with these two carbonyl formed. The result will be compound contain 3 membered rings. You should work on this solution of these reactions, the solution of these problems, by writing every step with the exact condition. Note that here two molecules. One molecule will react with this side and another molecule will react with this side by aldol condensation. Number C, we consider the following slide for number C. Here is another example of aldol cyclization reaction, intramolecular aldol reaction. So the potassium hydroxide will remove proton from here, this side of the carbonyl group. This enolate attack the carbonyl, a ketonic group, another ketonic group, to form 6-membered beta hydroxy ketone, which will dehydrate to form the alpha beta unsaturated ketone, or can be remained as alcohol, or can be exist as alcohol if the temperature somewhat high. We obtain the alpha beta unsaturated ketone. Note that the theoretically possible formation of enolate of the another side of the ketone group can theoretically lead to the 4-membered aldol addition product. But because the 4-membered ring is too unstable to isolate, to exist, the equilibrium shift towards the formation of the much more stable 6-membered ring. Again, note that all these reactions except the dehydration are reversible. Equilibrium, formation of carbonyl here, from here, and the attack of this ketone, and the possible formation of the carbonyl from here and the attack this ketone. All these reactions are reversible. That's to say, are in equilibrium, and the equilibrium shifts toward the formation of the more stable product, in this case 6-membered ring. Good luck.